Hey friends, welcome to another video of training. Today we're going to be going over and learning about schematics. Yes, I said it, schematics. To many of us, it might be intimidating. At first, when we look at them, we're thinking, what is this gibberish? But I promise you that by the end of today's video, if you watch every single clip, and before you move on to the next clip, you understand the previous clip, you will at least have a basic understanding of schematics. And there's really two kinds of schematics. You have what is pictorial and ladder diagram. Most of our time is going to be spent on the ladder diagram because if you understand this, you understand pictorial schematics. And we have two guests today that are going to help us understand schematics, and possibly four, but we have Mario and Peach. They're going to help you understand how schematics work. Are you ready? Let's go. Okay, so before we go into the schematics, it is important you understand the concept of a bridge. Now, have in mind, if you go to the Golden Gate Bridge in San Francisco, the bridge on 6th Street in Los Angeles, or the George Washington Bridge in New York, or whatever bridge you go to, a lot of the times you don't have a bridge that opens up and closes, right? So this is just to help you visualize it. Because now bridges, for you to go through, you just got to pay money, right? But you get the point that I'm trying to bring out here. If the bridge is open, right, and you literally have the part that normally is down, but it's up and it's open, just like a door, then Mario cannot make it to Peach because he's stuck over here. If the bridge is closed, right, it closed, then Mario can travel and make it to Peach. So that's the idea with electrical. When something is open, power cannot go through because it's stuck. It is open. When the bridge, the switch is closed, then power can go through to its destination. And I feel like a lot of people get confused with this concept because if something is open, then hey, the grocery store opened up. Now I can go get my groceries. If the door to my bedroom is open, hey, it's open. I can go inside and go to sleep or do something. And when something is closed, we tend to compare that or assimilate it to something that's negative, right? If something's closed, I cannot make it past my bedroom because it's closed. Or the grocery store closed. I can't go and get my groceries anymore. You see, the connection is negative. But we have to now think differently with electrical. If something is open, then hey, power is stuck over here. Mario cannot make it to Peach because it's open. In electrical, if something's closed, my switch, my bridge, my contact, it's closed, hey, I can make it through. And of course, we're not going to go into meters too much. I'm just going to show you the concept of having a path or not having a path. And to do that, I have an alligator clip, okay? This alligator clip right here, I put this on continuity. So I'm going to go ahead and test it, okay? So all I'm going to do is put this lead over here, right? And this lead over here. And you see, you might not be able to hear it, but you see it went from not having a light to having a light. So now I have a path from here to here. Great. What happens if I cut it? You see that turned off. I don't have a path anymore. It's open. This is another example. And you probably see this every day, right? A light switch. That's off. Flip it up. That's on. So right here, simple illustration, but important for you to understand. Right now, I have it on the off position. So you see my meter, I don't have a beep. I don't have it on. I don't have a path. It's as if Mario was down here and Peach was up here. For Mario to go to Peach right now, well, he can't. It's open. And actually a better example of that right there. Okay, so when I check continuity, you see, I don't have a beep because it's open. Once I close the switch, you see that light? It turned on and I have continuity. I have a path. So now I went like this. And that is why in your room, when you flip the switch, you're sending power through to turn on the light bulb. So hopefully this made sense because now we are going to go deeper into other symbols and other switches that now react with the temperature and pressure. And if you understand that, it'll help you understand how schematics work. Okay, so we're fast approaching the big schematic that we'll be using with the package unit, but it is important that we understand temperature switches. Also pressure switches, which we're gonna go over after this very briefly. And then we're gonna go over a live circuit. And with that live circuit, we're gonna draw it on the whiteboard. And so you have a better understanding. And then we'll go into the big schematic. So we have temperature switches. Now, these temperature switches, of course, you can see them in furnaces, you can see them in different applications. In this case, we're gonna associate those temperature switches with your thermostat. Now, of course, I'm not gonna go too deep with the wiring. Some basic understanding will help with this. But if we were just to briefly go over it, my red wire, that's my R, that's power. My yellow wire is my Y, that is cooling. My white wire is my W, that's heating. My green wire is my G, which is fan. And then my blue wire is my C, which is common, okay? But internally, we have a temperature switch, if you want to see it that way. And this reacts with temperature. So just to kind of give you an example, right? Going back to the switch here. Right now it's off, it's open, right? The bridge is open, right? Mario and Peach are not together. Boom, I just closed the switch. Awesome, Mario and Peach are together. So just imagine this temperature switch. It is very sensitive to temperature. Let's say it's a temperature switch, rather a switch that is sensitive to temperature. So if I were to do this, and let's say it is a close on rise, open on fall, okay? So we're talking about a close on rise, open on fall switch, a temperature switch. So if I go, I'm introducing hot air to it because it's sensitive to temperature. And we just said, it's a close on rise, open on fall. So if temperature rises, the switch closes. If temperature falls, meaning let's say I'm not introducing hot air anymore, it's gonna slowly just default back to open. That's all we're doing with a temperature switch like this. If we're dealing with a temperature switch, which is the opposite, you see, this is a close on fall, open on rise. So let's say I have a block of ice or dry ice, and I blow through it. I'm introducing cold air now. We just said that it's a close on fall. If temperature falls, because I'm blowing cold air through it, it closes. And if now temperature goes up, right? Temperature goes up, there's more heat, right? The switch opens. So that's the concept. That's what I want you to understand before we move on with the thermostat here, right? With this temperature switch, if there's a rise in temperature, boom, closes. If the temperature drops, it falls. In this case right here, if the temperature falls, it closes. If the temperature goes up, it opens. They're both different temperature switches, but it's still a switch. If I want to go from here to here, it's going to be based on temperature, based on which temperature switch we're working on. So let's go to right here, right? And this one here is going to be cooling. This one's going to be heating right here, okay? Cooling, heating, okay? So let's say in your house, the temperature is 80 degrees in your house. And the set point you have it at is 74. My 80 is greater than 74. It's too hot. And we just said what kind of temperature it is. If temperature rises above the set point, it's gonna close. But it does it internally. And what it does, it closes the contact between R and Y. And this is another way of seeing it. When something is open, this is what you'll see on the schematic. You'll see like a parallel line with two lines that go. That's open. So in this case right here, Mario and Peach, they're not together. Right here, how I drew it in the previous clip, if it's closed, you just see a line going through it. Mario and Peach are happy and they're together. So when I'm in cooling, right, for example, on this one, R and Y touch each other. And of course, we're not going to go too much into this. I want to go more into the concept of a bridge, okay? So in this case, right here, when the temperature inside the house is 80 degrees and you have a set point of 74, it's too hot. It's a close on rise. That means my temperature switch is going to go like that and look like this. This line like that, boom, made contact. Hey, it's too hot. I'm over here now. And so what it does with your thermostat, R and Y basically make a contact with each other. Boom. Turns on the compressor and calls for cooling. But it does it, of course, internally with the thermostat. Look at this one here. Temperature in your house is 70 degrees. You have a set point of 74. Is the switch going to open or close? It's gonna stay open. It's not gonna close because we're just seeing right here, my set point 74, the house is kind of cold. Why am I gonna turn on the air conditioning system? So it's gonna stay open. It's only gonna close when that temperature goes up because it is a close on rise temperature. So right now it is an open on fall, meaning that we have not exceeded a 74-degree set point, so it's gonna stay in the open position. Mario is stuck over here. He wants to go to Peach. He can't because he is stuck on this side. It is open, right? Like an open bridge. And so I just drew it right here, right? When it's closed, you see right here, that little line right there, the little line is touching this little circle. It's closed, right? On temperature rise, it closed that contact, the little bridge. So I have a path between R and Y. When it's open, R and Y, it just stays open just like that because I didn't exceed the set point. It's just a switch, guys. That's all it is. It's just a switch. It's just that the thermostat reacts with the temperature of your house. What do you really want to pay someone, or what do you want to be at someone's house just doing this the whole time? Where, let's say you have R here and then Y on top. Don't get me wrong, that would work. If you go, okay, you want cooling, Mrs. Applebottom? Great. Boom. You get cooling. No more cooling? Okay, stop. You want some more cooling? Okay, boom. Okay, I don't want no more cooling. Let's open that. The thermostat does it for you. It already has these internal temperature switches inside. All right, for heating, it's the same concept. It's just the opposite. It is a close on fall, open on rise. So going back to this example here. My set point, and we're talking about the house, let's say, being cold, right? Okay, so obviously this mode here wouldn't be during the summer. It would be during the winter. So my thermostat, I put a set point of 72. Inside of the house, it is 68 degrees. Is that bridge gonna stay open or close? Well, we just said, if the temperature falls, it's gonna close. I'm not at 72. I want the house to be at 72. It's still too cold. So yes, it's gonna close that bridge internally between R and Y, and you can see it right here. Now the line is touching this circle here, it's touching that circle. Now I have a bridge that is closed. And my R sends power to my W to get heating because it's too cold. And the same concept is with this one down here. If my set point is 72 and it hasn't changed, but now the temperature inside of the house is 76, is the bridge gonna stay open or closed? It's gonna stay open because I'm not below 72. We just said, if the temperature falls, in this case below the set point, go ahead and close. But the temperature rose, so it's gonna stay open. I don't need a call for heating. And in that case, the bridge between R and W stay open, and that's how the temperature switch would look like if you're able to see it within the inside the thermostat. But do you understand the concept here? It's just a switch. That's all we're doing. It's all a switch. In all these scenarios here, based on temperature, either we're gonna have a path, right? And in this case, it's R and Y, Mario and Peach. If it's closed, boom, I have a call for cooling. Great, I'm happy. But if it's open, there's no call for cooling because it's open. I'm already satisfied in this case. With heating, if it's too cold, Yep, I need heating. R and W touch each other. Boom. Now I got heating. Mario and Peach are happy. In this case, though, the set point is 72, and I have a temperature inside the house that's 76. Well, I don't need to heat the house anymore. I'm already past the 72. I'm gonna stay open. So hopefully this makes sense, because we're gonna go now into pressure switches really briefly, and then we're gonna go into a live circuit. And then with that live circuit, we're gonna draw the schematics, symbol by symbol, line by line, and then we'll go into the big schematics with the package unit. Okay, I promise this is gonna be the last switches that I introduced. I know I've been talking a lot about switches, but I promise you, if we understand how switches work, how the concept of the bridge being open or closed, it's gonna help you understand how schematics work. So if we've talked about temperature switches, right, and they have to do with temperature, now let's talk about pressure switches, and these have to do with pressure. So think about it in your air conditioning system when it's in cooling. Your condenser, your high side of the system, higher pressure. Your low side of the system, low pressure. And of course, there's certain things which we'll talk about briefly that can cause the high side pressure to go up a lot higher than usual, which is not good. And certain things on the low side of the system and your evaporator that can cause the low side pressure to drop a lot lower than usual. But these pressure switches, they work the same as any switch. It can be this switch, it can be the temperature switch. Either I have a path, right? Because I only have 2 wires, right? And then the switch. Either I have a path going through or I don't have a path. Either it's open or it's closed, right? Just like this, right? Either it's open or it's closed. And to emphasize, if it's closed, the bridge is closed, power can go through. Mario and Peach can be together if it's closed. If it's open, I'm stuck over here. Mario's stuck over here. Can't go to Peach. Okay, so pressure switches. So this one here, the one at least that I'm holding in my hand, is a high pressure switch. It is a close on fall, open on rise. So right now, I'm gonna be reading continuity. There is gonna be a path from here to here. The switch is gonna be closed. And I'm gonna go ahead and just confirm, put it on continuity. And you see the little light right here on my meter. You might not be able to hear it, but you see, it's closed. I have a path because it's a high pressure switch. This high pressure switch, the only reason it's gonna open, right? Going back to this, the only reason it's gonna open and it's gonna be like this, right? It's gonna stay open is if my pressure rises. Did you catch that? My high pressure switch, it's gonna open if my pressure on the high side of the system rises. And how would that pressure rise? And have in mind, these do have a number, I believe. This one here, it's 550 or 650 PSI. So let's say it's 650 PSI or 600, whatever it's rated, and you gotta, read it. If that pressure goes really high, it opens to protect the system. And we're gonna go over it on the schematics, but when you call for cooling, your Y, your action, your 24 volts travels through this. So if it's too high because you have a dirty condenser, it's overcharged, it's doing its job, the pressure's too high, so the switch opens. Now power is stuck over here and it turns off the compressor. That's it. Let's say you clean the condenser, you remove the extra charge. The pressure is gonna fall down, and we just said, when your pressure falls, it closes. Now I have a path to go through. And the same is with the low pressure switch. And just for giggles, let's just pretend this is a low pressure switch. I don't have one in hand, but I'll show you how they look like right now. With this one, your pressure switch, it closes on rise. It opens on fall. Guess what? If your system is undercharged, or let's say it has 0 PSI, the system's not gonna turn on because it's doing its job. It's gonna open because the pressure fell. I have no pressure, and sometimes they're at 35 PSI, 34 PSI, they're all different. But if the system's undercharged or you have low airflow, because remember what happens with no airflow or low airflow, your suction pressure drops. So as your suction pressure drops, we just said it is if the pressure falls, it opens, right? Going back again to the concept, it opens, meaning that Mario cannot go to Peach because the bridge is open. How do we get this low pressure switch to close so they can be together and be happy? Or my action, my 24 volts, my Y can go through? Simple. Let's raise the pressure, right? Because we just said it's a close and rise. How do we do that? Well, it's simple. We just charge the system back up. If it's undercharged or if it's low, of course, you would find the leak and fix it. If it's low airflow, we'll clean the filter, open the supply vents. That's going to pick up your pressure, and then it's going to close, and then it's going to look like that. And the way the pressure switches look, let me kind of show you. You see right here. You see right there, that's my discharge line coming out of my compressor. And there's my high pressure switch right there. And then my low pressure switch is on the suction line. Do you see it right there? Right there. Okay, you see right there? Low pressure switch, high pressure switch. So now that we more or less have an understanding how low pressure, high pressure switches work, your temperature switches also work. Now we're gonna go into a live circuit. We're gonna draw it on the whiteboard, and I'm gonna briefly explain how a circuit works. And if you understand a switch and how a circuit works, you're gonna understand schematics. Friends, thank you so much for your patience. I know this video is a lot longer than usual, but I'm really trying to emphasize switches and now what makes up a circuit, which we'll briefly go over. But if you understand these two things, when we go over to the schematics, it's gonna make sense. It's just gonna click for you. So if you understand these two concepts, it's gonna click for you. And I want it to be easier for you because schematics can be hard to understand at first, but they're not that hard once you understand the switch concept and then the circuit concept. So to have a functioning circuit, you need three things. You need a load, you need voltage, and you need a path. So what's an example of a load? Well, a light bulb, a fan, a compressor, a laptop. A light bulb, you send power to it, the light turns on. A fan, you send power to it, it spins. The compressor, you send power to it, it pumps. You send power to the laptop, it charges. And although we're not gonna go too much into the meters, how to use a meter, but the way you use a meter, at least with the load, you check it with ohms and resistance. A lot depends on what load you're checking, but this is the one you would use typically. The second thing is you need voltage, potential difference. What is that? Well, you know when you're about to go to sleep and you charge your phone before you go to sleep into your outlet, the socket, that's potential difference. That's voltage. And in our case, in the United States, it's 120 volts. And other places in the world, it can be a different voltage, but typically you'll find 24 volts present on an air conditioning system. On your outlet power, it'll be 120 volts. And then we also have 240 volts going to a condenser. But you see the potential difference, the voltage varies. But an example of that would be our outlet power, 120 volts. And then three, we need a path for the current or the electrons. And this is what really makes things work, this right here. And to kind of give you an example, a simple example of a path, right, for your electrons to travel, you see this thermostat wire here. That's a piece of copper here. You see right there. And then this alligator clip right here, I stripped it, and you have this conductor here. And so the copper here, this part here, not the insulation, not the red and yellow, but this part here inside, that's where electrons travel back and forth. And you can think of electrons as just little balls right next to each other. And so in the United States, electrons, at least the alternating current in this case, travels 60 times a second. That's 60 times a second back and forth. That's really fast. Like for example, this light right here, alternating current, the little electrons are traveling back and forth 60 times a second. And you would think I could see it flicker 60 times a second, but it's so fast that it's just solid, right? So that going back and forth 60 times creates a magnetic field, and that magnetic field is what turns things on. So really, the reason why we need a load and a voltage, and of course we need a path for the current to travel, is so that we can have that current going back and forth, and it creates this magnetic field that makes the things turn on and work. Okay, so in the case of the load, you're gonna check resistance, and in most cases voltage. You check VAC on your meter, and in a path for your current, you're gonna get your clamp, and you're gonna check all amps alternating current. Okay, but going back to this example, and this circuit here, you're gonna see it on the training panel that I created. You're gonna be able to see it. Okay, so do we have the three things that make up a circuit? Okay, we have, and we're gonna use transformer. We're gonna use 24 volts as a source. We're not gonna use 120, at least in the case of the training panel. So we have our transformer, so we have 24 volt source. So you always need, at least in single phase power, in this case we're talking about single phase, but you need 2 wires, right? And it takes 2 to tango, right? That's the saying. It takes 2 to tango, right? So we need 24 volts. We have a hot and a common. We have Peach and we have Mario. It takes 2 to tango, right? To do a nice dance, to make things happen, okay? Okay, so we got power, we got a voltage, potential difference. We have the wire, right? The path for the current to go back and forth 60 times. And we have a light bulb, which is my load. So yes, do we have all things? Load, path, potential difference, or voltage. Yes, we're good. We have it. So since Mario, you see there's nothing stopping Mario from reaching the load right here. There's nothing stopping it, okay? He's right there already in the load. He already made it. Peach, however, though, she's stuck right here. She's stuck. If I were to do this, though, turn it on, it does that. Yes, I made it over here. And once they make it, they're so happy that they're going back and forth because Mario loves Peach. They're going back and forth, back and forth, back and forth, 60 times a second, 60 times a second. And that current going back 60 times a second, depending on the load, but at least just for simple terms, right? Because you have loads that are inductance or resistance, but we're not going to get into that. But just understand that they're so happy because they're together. They made it right there to the load. They're going back and forth 60 times a second, creating this magnetic field, and it makes things happen. But because they're going back 60 times a second, they're happy. But if I turn this off, boom, Peach is down there already. That switch, I turned it off, it's down there. And this is important to understand, okay? And I always use this as illustrations, okay? And I'll go over 2 illustrations, and hopefully one of them makes sense. The one I'm going to tell you right now, I just thought about it. The other one, I use it always in my lessons. The second one might make more sense. But let's say Mario was, I don't know, Mario was cheating with Rosalinda. Okay, I think that's her name. Mario was cheating with Rosalinda, but it's a lie. Luigi just started to talk smack about Mario. So, but Peach just hears the rumor. Hey, you're cheating on me with Rosalinda. I'm angry at you right now. I'm really upset at you. So, Mario's over here. And so they have to make it to the load. They have to make it to the castle so that Mario can give his explanation. Guess what were to happen if Mario were to just go right here and talk to Peach about it? Nuh-uh, they're going to fight because they can only talk about it at the castle, right? Before that, Peach is going to be fighting with Mario, okay? They're going to be fighting. And that is why, and this would be an example of a dead short to each other in the electrical world. But we'll get into that right now. But Peach finds out, hey, you're cheating with me, Mario, but it's just a lie. So Mario is right here, ready to explain his situation to Peach. You send power through. Hey, I'm not cheating with you. Luigi was lying. Oh, I'm so happy. And they start going back and forth 60 times a second. I'm so happy. Thank you for loving me. Okay? If that illustration doesn't make sense, maybe this will. And this is the one that I explained to the students. Imagine In this case, well, I know you see Mario and Peach, but imagine it's two gang members, okay? I mean, I don't want to specifically call out any gangs because I've never been part of a gang and don't plan to be, but I'm sure you've heard of the Bloods and the Crips, right? And so let's say, okay, and this is just to use the example, okay? Okay, so here, the Bloods and the Crips, these two gangs, right here, this is Homeboys Industries, okay? This is the rehab center. But before they make it to the rehab center, if they see each other out in the street, they're gonna fight, right? They're gonna fight and do crazy stuff, right? They're gonna fight, okay? Boom, 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 boom. They're gonna fight, right? Right here. Even if it happens before the switch or after the switch, if they see each other before they go to Homeboys Industries, before the rehab center, they're gonna fight, right? Even if it's before the switch, boom, 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 or after the switch, boom, 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 boom. They have to go to the rehab center. They got to go to Homeboys Industries, and there they already know what to do so that they can work together as a team, and then boom, they make things happen. Boom, 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 boom. Right? So that's the explanation. At least I like to explain. Two gang members, they cannot see each other. They can't stand each other. They must meet at the load, one on this side and one on that side. They're at Homeboys Industry at the rehab center. Now they can work together. Yeah, this is what you do. This is what you got to prevent. You got to be patient. You got to develop these qualities. And now they can work together, and then they can make something beautiful happen. In this case, the light bulb turn on, or at least work together peacefully. So that's kind of the example. And hopefully with the training panels, we're gonna go over it. It will make more sense, right? But there's three things to a circuit, okay? And there's a switch here, right? We have our volts, our source, our potential difference. We have the wire here with copper inside, which is my path. And then we have the load. And in this case, we're using a light bulb. Okay, so now let's see the simple schematic that we drew now on a training panel here on a board. So we need three things, right? And we already talked about it, right? We need the potential difference, my voltage. We have a switch, we got wires, and then we have a load, okay? So right here, this is what we got. So this is what I did. I am supplying it with 120 volts, and I have a transformer that converts the 120 to 24 volts, okay? So here, this is what we got going on. So the schematic that we drew on the whiteboard, it begins right here on my blue and on my yellow, right? Because it takes two wires, or it takes two to tangle, okay? So here, if you follow Mario, and let's zoom in a bit, okay? So this is my load, and this is my path, right? It's just copper inside. So you follow Mario, Mario has a complete home run path, you see? He's going, he's going, he's going, and it goes to my light bulb, which it gets wired up right here. And this is a 24 volt light bulb. It's not 120 volts. So it's 24 volts. So Mario already made it. I'm like, hey, Peach, where are you? I love you. Oh, I love you too, right? Oh, actually, in this case, we're gonna talk about the Bloods and the Crips, right? So the Bloods and the Crips. Hey, what's up? Where are you from? You know, if I have a chance to get to you, you're gonna get it, okay? So and of course, remember they cannot talk to each other. They must meet at Homeboys Industry, at the rehab center. They have to meet right here, okay? So I have, going back to now Peach. Peach now, she's going from here, from the other one, right? So this is common, and that's hot. So Peach is going here, right? It's just a wire. Boom, 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 boom. And now she makes it to my switch, okay? And she's, and the bridge, is it open or closed? If it says off, it's opened. I can't go through, right? Peach can't go through. But she's like, watch, just watch. I'm going to get to you. And then I flip this on. My light bulb turns on, and Peach goes through. And then they're able to work together. Oh, I didn't think, you're actually a lot better than what I thought. You're actually a cool person. And then current right now is traveling 60 times a second. 60 times a second, back and forth. And you see, it's creating energy. It's creating the light bulb to turn on. Only because they met over here. right? So look at what happens though. If now somehow this wire, I don't know, it could have nicked and exposed the copper, and maybe it's touching this copper here, right? Because remember, we don't want them touching each other, or the Bloods and the Crips messing with each other first. They must meet at the rehab center to work together. So look at what happens if it does happen. So I'm gonna go ahead and expose this wire here, okay? So you guys can see, remember, current is energy, it's heat. So I'm gonna go ahead and put it right here, and I'm putting it over here. So I'm getting constant power because my switch is open, so my power is stuck right here. But this is just to show you an example. Look at what happens. You see that? They're gonna fight. They're gonna fight. They don't like, they must meet at the load. And this wire actually feels warmer now because it doesn't know what to do. And if I leave it there, this is just gonna melt. So right now, you see the sparks? Not good. So that is a dead short to each other. Um, so and typically, and we can kind of go over it briefly, but on my common, this is also grounded, and just pretend this is wood, but just pretend it's metal, okay? Just for a minute, guys. Pretend this is metal. So typically the common is grounded to this because what happens if this wire here, right, the one that's carrying the 24 volts, touches the metal? Well, it's like the metal is touching the common because it's grounded, but it's to protect you, it's to protect itself, and it'll usually trip a fuse. If it has a built-in fuse or a fuse popper or a little fuse, a 3-amp fuse will go bad. But yeah, typically there's two types of shorts: a short to each other, right? Where they saw each other before they made it to the rehab center and they're fighting. They're fighting, or because now my common is grounded to the metal. Let's say this, because of a vibration, right? It exposes the copper and now it's touching the metal. Well, it's the same thing as if it's touching common, right? Hot is touching common because it's grounded, and you'll see that on the unit. But do you get the point, right? Just kind of going back just to the basic principle here, right? We got Mario, and Mario, there's nothing stopping Mario, right? He has a path all the way over here. He's ready, right? And he's ready to explain that he's not cheating on Peach with Rosalinda, but she doesn't know that, and she's upset. And so once she has the path to go through, she makes it. Oh, you do love me, and they are happy, and they're working together. And electricity and alternating current is traveling back and forth 60 times a second, and making something turn on. So that's the whole point. We want the power to make it to my load so it can make things happen. And that applies for your condenser fan, your indoor fan, your compressor, whatever it is you want to turn on. Anything really you want to turn on. It takes two to tango. So you want to make sure you come here and then boom, it goes back and forth. But remember though, right? The Bloods and the Crips, right? They're going to fight if they don't make it to Homeboys Industries, to the rehab center. They must meet each other here, not before, because that's a short to each other. As you already saw, what happens, right? They're going to fight. They're going to fight. And so you want them to meet at Homeboys, not before. And so hopefully this helps you understand the concept of a circuit, that you need three things: a load, you need a path for your current to travel back and forth, and you need power, you need voltage, because voltage is potential difference, right? And it's doing, once it makes it here, you have this potential difference 60 times a second. So current is going this way, foof, boom. You can see the little balls just going down, up 60 times a second, and that's what makes things happen. So now, finally, now we can go to the schematic and work with the unit. Now that we have a basic understanding of a circuit and switches. I almost forgot to talk about contactors, and I promise I'm going to be brief on this, but it is important to understand this component because it is on the schematic. But contactors, they come in different shapes and sizes, relays as well. But at the root, they're just switches. So if you understood the concept of a switch, are you going to be able to understand contactors? But for example, let's take, for example, these two contactors right there, Okay. All the contactor is, if we were to look at it, and let's see if we can get closer. Okay, so you see you have one pole and two poles. So this has two poles. I like to refer to them as freeway lanes. Like in a highway, you got a one lane and a second lane. This one, you got a one lane, two lanes. So you got two lanes here, two lanes here. But if you look carefully on this lane here, there's nothing interrupting power. It's just a straight path from here. Boom, boom, boom. You're there. On this one, though, to go from here to here, there is something in between. And this is just a bridge. It's open. It's open, meaning that if I have power coming here, for me to go from here to here, I need to close the bridge or do that. Okay, and that's the idea behind this. And the contactor is similar to this one, but this one here, both poles are interrupted by a bridge that's open. And for it to be closed, either I have to push my finger and push it down, and now I have a path from both poles from here to here, right? Or, and of course, this is the way to do it, is by sending 24-volt power on the side right here, right there, and right there. That's my coil. So if you want to keep it simple, and like this is the way I like to explain it, you got to pay $24. It's like going through a bridge. You got to pay a toll. You got to pay $24 so that you have access, so that the bridge closes because you already paid it. It closes so you can go from here to here. And the way you can confirm that, right? I have my meter, right? So if I were to put that on continuity, right, you can see the light. So if I'm going to go from here, from here to here, or let's try this one here. This one to this one here. You see, it's open. I'm going to push this. You see, now I have a path. But so, you're not going to be, because this contactor we use when we have a call for cooling, you're not going to be saying, Mrs. Applebottom, can I, do you want cooling? Yes. Okay. Thank you. I'm okay now. I don't need no more cooling. And then 30 minutes later, I need some cooling. And then you're going to push that. You're not going to be doing that, right? And that's too much work. So this is where you use a thermostat to redirect the 24 volts to go and send power, as we will see in the schematic, okay? But just to do this briefly right here, right? So, and actually before we move on to showing you the coil that's in here, right? And I don't know if you can see it. Let's see if I could, but these right here have coils inside, and they're like this. You see that coil right there? That's a coil. It's just a wire going from here, like from there, and then it's looping around a lot of times, and then it comes on this side. Remember what we talked about current? When current goes back and forth 60 times a second, right? It creates a magnetic field. And then in this case, when it receives 24 volts, it creates a magnetic field that acts like a magnet, and it pushes down. That's the way the contactor works. That's the way the relay works. We send 24 volts to the coil so that I can have power going from one side to the other side. That's it. We pay $24 or send 24 volts so we can go from one side to the other side. That's all we're doing with contactors. So for example, this one, we want Rosalinda to go from here to Luigi, right? We're not gonna put her on this lane. We're gonna put her on this pole, on this lane, okay? Follow Mario. Mario, if we follow the 24-volt source, you see there's nothing interrupting Mario. He's already here. He's like, all right, Peach, I'm ready. Come on. And Peach has to make it on that side of the coil of the load, because that coil is a load just like a light bulb. It's a load. It takes power. The coil is not a switch. This is a switch, but not the coil. It needs power. It needs a hot and a common. So if we follow Peach, she's going to go and go through the wire here, right? You see the other wire? She's going through, she's going through, she's going through. Oh, she's stuck right here. And this is how the cooling works. When I have the thermostat and I have a call for cooling, remember, if it's a close on rise, temperature rises, it's too hot, the switch closes. And now I have power over here. Now I have 24 volts. Current's going back and forth, back and forth, back and forth. And we can confirm that because you can see it right there. You see, I'm going to take that off. You see you see that just popped up? I'm gonna give it 24 volts again, you see? Let me go ahead and do that. Okay, there we go. So you see, and I actually do it from the switch. No power, power, no power, power. But now that I have power there, that's what we're doing. We're sending low voltage so that we can close the bridge, and then high voltage can go through to turn on the compressor. In this case, Rosalinda can meet with Luigi, right? So if you understood that, right, the high voltage is already wired for you. We just gotta troubleshoot the low voltage. And so right now, we just went from, right, and you can see it right there, from open, right? Let's open it. So on the schematic, keep an eye on this, okay? For the contactor, that's open. I'm gonna send 24 volts. Boom, closed. Because now Rosalinda is with Luigi. Now I have a path from here. Ooh, I saved there. From here to here. So we're using low voltage to close the bridge, so power can go from here to here. That's all we're doing with contactors and relays. Okay, now, finally, we can go into the schematics. Thank you for your patience. Okay, so the big thing when it comes to ladder diagrams is differentiating the high voltage from the low voltage. And how do you do that? Well, it's simple. You have a transformer, and this is the symbol for transformer. It looks like two clouds kind of approaching each other. But that's the symbol for transformer. It will tell you which one's your high voltage. Right on top, you see 230, 208. That's your high voltage up there. And on the bottom, you got your common and your 24 volts. This is your low voltage. So your low voltage is like your thermostat, right? Your high voltage, it's your indoor fan motor, your compressor, your condenser fan motor. And really, whenever you go to a job, unless it's a hack job, you had someone just come and just take all the wires out, then of course it wouldn't be wired as it should. You do have sometimes people that could put the wire on the wrong place, but if it's a new unit, all this right here, it's already wired up on the system, and I'll show you right now. The high voltage is already wired. You don't even have to worry about it. The only really two things you have to worry about is landing your high voltage, right? You got your line 1 and your line 2 and then your ground. So where is that on the actual unit? Well, it's coming from here. This is your high voltage, right? This is coming from your breaker, right? From your panel there. And then it goes to my disconnect. And then it goes, at least in this case, you got two thick wires that go on that side of the contactor right there. And if you look carefully, that is let's see if we can get close. That's what you see on the bottom. This is 11 right here for this black wire, and on top, 23. And then if you go across, right, because it's just a lane, it's just one pole. This is one freeway lane, 23. On the bottom, 11, and then it's 21. It's not 11. I'll show you why that's the case for that contactor. And then we've gone over it on the previous clip, right? You got your low voltage, your common, and your hot, your 24 volts. Mario and Peach. So we'll go over that right now. So when you actually look at the contactor here, and this is where it can be a little bit confusing. With your contactor, this part here, remember we said 11 and 21? So on this part here, this is just another contactor I got. This one's 11, right? So 11. And then this one here is on this side, 23. So 11, 23. So we said that 23, with the 23, you had 23 on this side and then 23 on top, if you remember on the other contactor. And why is it that we just have 23, 23, 23? Because when you look at it, when you look at the contactor, there's nothing in between. It's just one lane. If I land power here, I'm gonna get power coming out over there because there's nothing in between. The reason on the bottom they put 11 and 21 is because you do have something separating it. You have a bridge that is controlled by 24 volts or $24 that you got to pay so you can push that in. That is it. That is why they put that one as 11 and 21 on the right side. So if you were to look at the contactor again on top, 23, you see, there's nothing stopping it. It's just full flow. Power's just going to go through. But 11 and 21, 11 and 21, that's it right there. This is an open contact. So as I had mentioned, if I want to close it, then yes, we can go ahead and draw a line close, which we'll go over right now, but I need to send 24 volts right here on the coil so that power can go through. But do you see the contactor, all the wiring, it's already there for you. You don't have to worry so much about the high voltage wiring. It's already there. Just to kind of prove the point here. This is my compressor, right? This is my capacitor. My capacitor, it says for the H, the Herm, it's a blue wire. Let's confirm that. So my compressor, you see that blue wire there? You see, it goes to the capacitor. And let's see if we can get a good picture of the Herm there. Let's see. I already discharged everything, so I am doing this save. You see, it's not the best picture, but let's see if we can get. It says a Herm, so that's true. The blue wire does go to Herm. What about this brown one? This brown one is my fan. You see, my fan. Go right here to my capacitor. Fan, brown wire, boom, to your condenser fan motor. So all this, it's already wired up. Very rarely will you have to do this by scratch. And if you do, just follow the colors, okay? And then have in mind, you're gonna have a legend that's on the bottom. This one doesn't have it. It's on my other one on the connection diagram. But you have a little legend what these stand for. OFM, outdoor fan motor. Cap, capacitor. Comp, compressor. DR, defrost relay. And then C is my contactor in this case. And you see these other things, a lot of the times we're not even messing with these things. In today's video, we're just gonna focus on the contactor, and so you can make sense out of it. So, like I said, high voltage, you see, it's already all wired up for you. It's already all wired up for you. This is all wired up for you. Even though it's crazy, it's already all wired up for you, okay? We're gonna focus more on the low voltage, so it can help you in understanding diagrams and troubleshooting. So like I said, okay, I got my transformer, and then I have a little 3-amp fuse, which I'll show you right now, and then my thermostat wire. So the little exercise that we're gonna do today, because this is a heat pump, we're gonna have a call for cooling. And I'm gonna use the little cards that we have here, Mario, Peach, Luigi, and Rosalinda, to help you understand that whatever happens on the low voltage has an impact on the high voltage. Okay, so I do want to bring something out, and it's going to make sense right now as I show you on the package unit. Your common coming from your transformer, right? Your low voltage, you got your 24 volts and your common. Your common, you want to ground that. How does that look? Well, when it comes here, and I'm going to go ahead and disconnect power. So look at so right here, so on top, you have what is your high voltage. Let's see if we can get a little bit closer. You see right there, 208, but you have a black, right? A black wire and a yellow wire. And that's good because it matches with this one here, yellow and black. Good. And then coming out of my low voltage transformer is red, and then a ground and yellow. So let's go ahead. Actually, and I missed something too. You actually have a ground and yellow. This is ground and yellow. The one going to the to your package unit, grounding it. But you have another wire coming out that is brown. Okay, so we got two wires coming out. So here we go. Okay, so there we go. Let's get closer. So yep, you got a red wire, right, coming out. And if you were to look closely on that, that is, I don't know if you can see that, but it says right there, it says secondary, right there, secondary, and that's 24 on the right, it says 24. And this one on the left, it says C, common, okay? So remember from the previous clips, we know that these two, even though they come out, when they come out, they cannot touch each other. You got the Bloods and the Crips. They need to go to a load. They need to go to something like the Contactor Coil, right? But look what they've done, and this is pretty cool. Coming out from the common, you got a brown, but look at this green and yellow. If you follow that green and yellow, it goes to, let's see, it goes right there. You see? it goes and it's grounded to the metal of the unit. That's smart. You want to know why? Because have in mind, this 24 volts, your red, it travels all over. That high voltage, that low voltage, 24 volts, it travels all over. But by me grounding the common, which you saw right there, if this wire right here, this red one, let's say it strips, and let's say it exposes a little bit of copper, and that copper touches the metal. Well, the whole metal, the whole unit is common because it's grounded on the common side. So it's going to pop a fuse. It's going to tell you, hey, we have an issue. And I'm going to show you right now an example. But just to kind of emphasize the point, you got 24 volts coming out, a red, which is 24 volts. You have a brown one, but then the ground is also on your common that goes to the actual screwed on right there to the metal. So the whole unit is common. So think about it. That 24 volts can travel through your pressure switches. It needs to go to your contactor coil. You got a low voltage going to your ECM motor. There's a lot of points of where it can strip and touch the metal. And then that's good because it's going to pop the fuse. If that wasn't grounded, you can have weird voltage drops. But look, this is what happens, okay? So I'm going to go ahead and put power, okay? And for this one here, just so you know, I did remove the fuse. So there is a fuse right here, but I removed it because I didn't want to pop that fuse over and over. I just put a fuse popper. So if this pops, goes up, is the same as this fuse popping or burning up. Okay, so what did we say? That the whole unit is common, and I'll confirm it. Look what I did right now. What I did, so Mario should be going right here, right? Because this is the contactor coil. They need to work together to go to the load and work together to then close that contactor, right? But let's say Mario decides to take a detour. He goes, boom, he goes right here, straight to the metal, right to the metal, to the actual package unit. We just said that common, we grounded it. So everything is common. So now we're gonna have Peach and Mario fight each other, right? Hey, you're cheating on me and you're fighting. We didn't make it to the therapist. Or Bloods and Crips. Hey, what's up? Where are you from? Come on, I'm gonna fight you. They don't make it to the Homeboys Industries, to the rehab center. And they're fighting, right? Because like I said, common is grounded. Mario decided to take a detour. He should have gone on this side to complete the circuit, right? Because it takes two to tango. But he took a detour, boom. He hits the metal part. So what he's doing, what that looks like is this. Let's say, and I actually did it specifically to the schematic. I got my R from my thermostat, right? Because I got 24 volts. And I'm going to go straight to the metal of the package unit. So look at this right here. And I want you to see this fuse popper here. Let's see if you can see that right there. Okay, that should be popping open. And then this right here. Because we said all this is common, the whole metal, because common is grounded to the metal. Let's see. Let's go ahead and see that. There we go. You saw that? It popped the fuse. You wanted to do that, and you probably saw the sparks right here, right? All I did was just kind of hold it in place because it needs to pull enough amps. I believe this one here is 3 amp. So you could, I'll do it again one more time. But you see the spark? You see that spark right there? That's the same if I were to get an alligator clip and then just go from common to hot, just like that. That would burn the transformer. But thankfully we have a fuse, right? A fuse before it burns the transformer. We have the fuse popper. But those two do not touch each other. They must go to a load. Yeah, right? They must go to a load to work together. But that's what would happen, you see? They're fighting. So that 24 volts travels through my system. Due to vibration, it can expose the copper and then it can be touching the metal. And if that happens and it pops the fuse, well, good, it did its job. If you don't have that common grounded, we run into more issues. You get like 18, 13 volts. You get these weird voltage drops because now it's not the common is not grounded, but the hot is stripped and touching the metal. You're gonna create resistance. You're gonna have these weird voltage drops. But look at this. Do it again. You see the spark? You see the spark right there? Right? That's heat. That's current. So if I leave it there, look at that. Right there. Right there. It did its job. So just understand that, because now we're going to go into the scenario when it comes to cooling, but we must not take a detour. The hot voltage, the 24 volts, must make it on the other side of the coil. And in this case, we have two different coils. We have the contactor coil and the reversing valve coil, which we're going to go over right now. But just understand that you want to ground the common so that it helps you in troubleshooting and it protects the system. And really, that's how all transformers should come, where the common is grounded. Okay, so here we go. Let's do the first exercise. Let's go ahead and power up the contactor coil, right? So if we send 24 volts here, right? It's like paying 24 bucks so that high voltage can go from here to here, right? It's gonna push that down. So how does that look? Well, we send 24 volts right here, it's gonna look like this. On top, it's gonna do this. Boom, just like that, right? Remember we talked about that earlier? So now there's gonna be a path from here to here, and it's going to complete the circuit for my compressor and my condenser fan, and it's going to turn those components on. So the way I did it right here, I literally bypassed this. So think about this, right? My source of my 24 volts is my transformer. For my common, right? Let's get a little closer. For my common, you see, Peach, it's going to go, she's going to go. There's no contact. There's no open contact. It's she's just going to go, 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 go. Go, go, go. She's already here. She's waiting for Mario, right? She's waiting for Mario to work that out, right? She's upset at Mario. Mario, though, he cannot go that route. He cannot touch the metal of the unit. He must take a path, right? So that current can go. Right? There's three things to a circuit. You need potential difference. You need the wire for the path, for the current, and then you need the load. So look what I did right now. I literally just went from here, boom, took a detour. I didn't even go to my thermostat. I didn't go to any other part. I just went boom, boom, took a shortcut, and I'm already here. Would that work? Ask yourself, is this going to work? Yeah, it's going to work. Even though I'm isolating the thermostat, it's going to work, but the air conditioning system is going to be on 24/7. So this is how it looks like right here. So right now, what I did, I got an alligator clip, and right there, I'm getting 24 volts, raw 24 volts. That's constant 24 volts. And then my common is my brown one. So the blue one down there, that is my 24 volts. Obviously, this blue one doesn't have any power because I'm not going through my thermostat. I'm not going through my pressure switches. I'm going straight from the 24 volt source to my contactor, and watch. That is going to turn on because I'm supplying it with 24 volts. So give me a second. You see that? That pushed. And how do we know? My condenser fan turned on. You might not be able to hear it, but my compressor turned on. That would work, right? That would work. Don't get me wrong. If your board is burned up, your wires are all messed up, you could technically do that, but this is just for like a 10-minute for you to see if it's working or not. Maybe if you know you're gonna get the board and the board is bad, you can bypass it so that maybe you can get the unit going on, just temporarily, even just for that day. If you leave that on, the unit's gonna stay on all the time. So we don't want to do that. So we're gonna go ahead and remove that, and we're not gonna take that path. So this is one way just to kind of show you that Mario can take this path, but it's a constant direct shortcut path because now he's not going through any switches and safeties, which we're going to go over. We're not using the thermostat in this case. He's just taking a quick shortcut to meet Peach at the castle, at the therapist, at the load. Okay, so now let's have Mario take a different path. So, right, Peach, common, there's nothing stopping her. Boom, she's got no, you don't see any of that, right? You don't see that. Let me go ahead and erase that. You didn't see that open contact. You didn't see any pressure switches, temperature switches. Common is typically home run. It's already waiting for Mario so they can, be happy and then have current going back and forth and making that load work. Mario, though, right now in the earlier clip, we had Mario go straight from the transformer, boom, to that load. That would work, but the system would be on all the time. So the way that we can do it right here is as follows, right? And this is another way, but just to show you, there's different ways of doing it, but this is not the right way. So Mario can do it this way, and on the thermostat, he can then take a detour and go to the load. Would that work? Sure, that would work. Not the right way, but it would work. And how does that look? Well, if you look down here, right, this is my thermostat wire. So instead of it going straight from the transformer, it's getting power from the same wire that's powering up your thermostat. Would that work? Yeah, that would work. But once again, your system's gonna stay on all the time. You see, you saw that got pushed in. Condenser fan turned on, right? So that would work. So what I'm trying to teach you here is that there's different ways to send your 24 volts, right? There's different ways that the 24 volts can travel to make it to the other side of the load, because Peach is already here. Common is already there. Common is always home run. If you were to follow this brown wire, right, that's your common. So let's see, if I were to follow that wire right there, yep, it goes to all my commons, and then the common coming out of the transformer confirms it because it's a brown wire coming out. The common on that one, you see, brown wire. And sure enough, it does go to the common. But this is the other way. Mario, or the 24 volts, you can bypass it. It will turn it on, but that's not the right way. So now we are going to do it the right way, and take a look and really pay attention to the journey that Mario takes to then make it all the way to the other side of the coil. Okay, so now I do have it wired up the right way, in the sense that we're gonna give Mario the correct path to take so that it can go through the safety switches, right? Pressure switches, temperature switches, to make it to my contactor coil. And I'll show you on the actual unit how that is being done. And this is really, on a lot of the units, that's how your 24 volts travels to make it to your contactor coil. So have in mind, this is a heat pump. So for this specific unit, we need to send 24 volts to 2 different coils, 2 different loads. One is to turn on the compressor, okay? So we know that we need to power up the coil, right? So common and hot, or it can be hot and common. It's not reverse polarity sensitive. So we got one coil, this is for my compressor, and this unit, we just said we need to power up the reversing valve to get cooling. So the reversing valve is right here. So if you look at that reversing valve, that right there, this the black thing all the way in the back, the little square, the little circle there, square, that's just the coil, just like your contactor coil. And it needs 24 volts and a common. Look at the brown wire. Brown wire, that's my common. My common is already there. It's not going through any safety switches. It's not going through anything. It's going straight from the source of common, from your transformer, going all the way home run right there. My 24 volts, the black wire, that's the one that we do have to take care of so that it can make it there and we can get cooling. So this is what we're gonna do for this example, okay? And this is the one where you really want to pay attention to, because this is how the 24 volts gets routed to call for cooling. Okay, so we're gonna have Luigi and Rosalinda be together. They're gonna be a team, and then Mario and Peach. So remember what I said, right? Common is already home run. So what does that mean, right? So for my contactor, right, my contactor, if you look at Peach's path, there's no switches. It's just home run. She's already there. She's already waiting for Mario to fix those marital issues, right? Because she's really angry, right? But Mario has to meet her here in the castle at the therapist on this side, okay? They need to be, and then once they fix it, once they work it out, they'll be able to work together, and that current will make that contactor, right? Pull in, boom, and then turn on the compressor. High voltage goes through, right? Because we're not messing with the high voltage. It's already wired for you. Okay, so Rosalinda and Luigi are working together. So Rosalinda, same thing. Look at that. If you were to follow the common, the path, right? Look at that. It goes through here. It goes through here. And in this case, and I know that it's, and let me go ahead and move Peach just for a bit, okay? I know it's a bit confusing at first, but the way that common takes this route. It goes like this. It goes like that. And although it doesn't show it, but internally, it kind of does this. If that were to kind of make sense internally. And yes, a lot of boards, I wish they would show you everything. But it doesn't matter because I know that you see right there that it says brown. That's also brown. My common is brown. All my browns are common. So, but that's the path that it takes. So my contactor coil, my reversing valve, they need common. Commons are already there, right? So we're gonna put Peach back over here on this side, and then Rosalinda right here. So they're ready to work out the marital issues with Mario and Luigi. They're ready. But now they need to take the right path, the right course to make it on the other side of the coil. Okay, so just follow with me, okay? We're gonna, if you want, we can go ahead and do what's easy first. We'll go ahead and do Luigi, right? So why do I say it's easier? Because of this reason. When you program the thermostat, right? We just said it's a heat pump. So your 24 volts has to make contact with my Y and with my O, right? With my Y and with my O. So in this case, it is the yellow wire and the orange wire, right? Yellow wire and orange. So have in mind for the yellow one, I just used the red one just because the red one stands out more. But for my orange, my reversing valve, I did use orange, okay? But it is important, okay? I emphasize, it is important that the thermostat has heat pump compatibility. It needs to have an O, and you have to program it that it is not a conventional furnace, that it is a heat pump. You need to do that. If not, none of this will work. Okay, so let's say we do all that. Okay, so let's take the path of, let's take the path over here, right? So let's just say Luigi's right there. And just for simplicity, I know it doesn't have it. I know that you don't see it like that on the thermostat. But like I said, when I have, just for us to understand the point, when I have a call for cooling, my thermostat, remember we talked about it in a previous video, my thermostat, right? Because the red is the main one. That's the master. That's the one that makes contact with all my actions, Y, O, G. So when I have a call for cooling, the thermostat will close that switch, that bridge between R, and let's just focus on the reversing valve first, okay? R and O, boom. And the way it does that is because the thermostat is like, okay, R, and then behind the thermostat, you got your O. So R is like, here you go, O, boom, closes the bridge. So now Luigi's supposed to make it to the reversing valve. Because I have a call for cooling and R gave 24 volts to O, look at that, follow with me. So now the bridge closes, right? The bridge closes. So let's go ahead and get closer. You see O, 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 okay? And even though on the actual board, and I'll show you right now on the board, it doesn't have that little wire, but the orange wire, your O, comes in here first. If that receives 24 volts, it then sends 24 volts out to my reversing valve. So that's what it does. Boom, boom, boom. Nice. Now the reversing valve has 24 volts. This is the important one though, Mario's route. Because I've been showing you that you can reroute Mario's path different ways, but we got to do it the right way, okay? So let's do it the right way. So let's go ahead and get closer. So Mario, go ahead, starts right here. Okay, this is important right here. This part right here goes right there, and then he's over here. He's on this side. He wants to go from here, right? He wants to go from here to there, okay? How can we do that? Well, you and I really don't have control over this because that's a temperature switch that is already built in on your thermostat. This is a close on rise, open on fall. So remember, if you have the mode on cool and inside your occupied space, it gets too hot, your temperature rises, okay, because your thermostat is the one that's going to do this, right? Then, boom, it closes the contact. The bridge, because it's a temperature switch. So this is my thermostat. This is my Y. So if it gets too hot, right? Close on rise, temperature rises. Yep, the thermostat closed the switch between R and Y. Mario goes through. So, okay, good. Mario made it over here. He's still not ready. He's still not in the clear. He's still far away from Peach. So he's got to go. He's got to go. And so, and I did forget to mention, okay, this part here, this is a 3 amp fuse. So before your 24 volts goes to your thermostat, it has to go through the 3 amp fuse, because in case hot and common touch each other, it blows up the fuse, not the transformer. So I did forget to mention that there's a little 3 amp fuse, which I'll show you on the board. So Mario made it through the temperature switch. He's already here, okay? And then he goes to the board. He goes to the board, and he's gonna go to the defrost board, okay? He's going to the defrost board, which, like I said, this is just to show you the ladder diagram. I'm gonna show you on the board right now. So he's making it. Why, you see? Oh, sorry, Mario got a little scared of Bowser. He's back in business. It's right here. So why, you follow it. It goes to my yellow of the defrost board. Okay, I'm right there. Internally, and of course you don't see this, and I wish they would show this, it comes out through my blue wire. Okay, so I'm gonna just move over here so you guys can see more. Okay, so now he comes out from your Y. So you see, he first comes in on this one, P1-5Y, which I'll show you right now. He comes in and the yellow wire in. Once the yellow receives 24 volts, the 24 volts then comes out from here. Mario's goal is to make it from here to right there. So you can be next to the contactor coil. You can be and with Peach working on that load, right? On that load together. But he's right here. So what does he have to overcome? He needs to overcome 2 pressure switches. Remember, we've gone over this, right? You have a high pressure switch and a low pressure switch. You have a pressure switch that closes on fall and one that opens on rise. So look at this right here. You got a low pressure switch right here and a high pressure switch. So we talked about it, right? That little clip previous. That's why it was important that I went over those clips before. But this low pressure switch, if the pressure drops too low because it's low on refrigerant, or you have a dirty filter, then guess what? That bridge, it's gonna be open. So right now, let's just say, just for the heck of it, right now, let's just say we have a good functioning unit, okay? So it's good. But let's say I'm low on refrigerant. So if I'm low on refrigerant, my pressure drops, or I don't change my filter. That's a low pressure switch. It opens on fall. If my pressure falls, open. It is open. We can do that too if you want right here. Just open. But let's say I charge the system up. I charge the system. It has refrigerant. I clean the filter. I have a path. Great. Awesome. Mario can make it through. Now he's stuck on here on the high pressure switch. That is an open and rise. So yes, that is normally close. There's always a path. But let's say my condenser fan is not working, or my condenser fan is, like I said, is not working, or my condenser is dirty. What's going to happen? Because he can't reject heat, my pressure goes up. It is an open on rise. It's going to open. Mario's stuck over there. He can't make it through. But let's say I clean the condenser, I change the condenser fan. Boom, Mario makes it through. And he's here with Peach now, working together with the therapist. And they're so happy that they're going, oh, man, I got to get better magnets. So now they're working together, going back and forth, creating 60 times a second. And that contactor coil, right? Boom, pushes in, completes the circuit, and then turns on the compressor and condenser fan. But this is what I wanted you to see. You see the path that Mario had to take? It wasn't an easy path. He had to go through the 3 amp fuse, right? That fuse has to be good. If not, he's stuck over here. But it's good. It's good. And then this needs to be wired right, programmed right. All that has to be right. And then if its temperature rises, boom, switch closes. He's going. He's going through the board. He's going. Oh, my low pressure, high pressure, they better be close. Clean filter, enough refrigerant. It better have a clean condenser. If it is, he's just going to continue going through. Boom. That's going to turn on the compressor. And on this case, my reversing valve, Luigi is already here. Now I'm powering up the Y and the O. And just because this is good, remember, I can have switches here that are not working. The system can not be working right. But if they both make it to their coils, now I have cooling. So now I'm going to show you on the actual unit how Mario and Luigi follow this road. So then it can kind of make more sense to you along with the diagram. Okay, so we've gone over the ladder wiring diagram. The ladder wiring diagram helps us to understand that at the end of the day, with the ladder wiring diagram, all we're doing is we're using low voltage to then close the bridge and send high voltage through, right? We were able to see how on the ladder wiring diagram, you had your low voltage on the bottom, high voltage on top, separated by the transformer. But that's the idea behind really the air conditioning system, any schematics that you're working on, whether it's connection or ladder wiring diagram, you're using low voltage to pay $24 or send 24 volts to then send the high voltage through that bridge and turn on the components that take high voltage. That's all we're doing. So in this case though, we're working with the cooling, right? A heat pump. So we need to send power to my reversing valve and my compressor, okay? So by now, hopefully the previous clip kind of gave an idea how the 24 volts where it travels to. The nice thing is that common's already at the coil. So remember, we're dealing with two coils, two loads, your contactor coil and your reversing valve. So we have here Peach, she's already here at this contactor coil on that side. So I did this pull disconnect, so there's no power. But brown wire, common, she's already there. She's waiting for Mario to work things out, okay? They got to work things out. And then over here, you got Rosalinda, that brown wire is common. She's waiting for Luigi to work things out, okay? So here we go. Where do we start? Okay, so I was able to pull the boards out. It's still a little bit messy, don't get me wrong, but just to kind of briefly go over it, that common and then that low, which is 24 volts in common, that is going to my ECM motor on the low voltage side. And then you see right here, this red wire right there, that red wire and that brown one, that's coming from my transformer. That is where the transformer supplies the board with 24 volts. And then that's my fuse right there, okay? And then my defrost board is on the bottom right here. But let's go ahead and talk about Luigi's path. Luigi needs to make it with Rosalinda so we can send 24 volts to that reversing valve, okay? So how does that work? Well, it's important, like I said, to wire up the thermostat and make sure it's compatible for a heat pump, okay? So we got my power, right? So, right, the skinny ones, we already mentioned, that's my thermostat, and then the red, the bigger ones, that's coming from the unit. And so that red one here, the big one, the red one, and then this brown one, the thicker ones, that essentially is coming from my transformer, 24 volts. Okay, so then we're supplying the thermostat with 24 volts, right? The skinny red wire. And then this skinny brown wire is my common to my thermostat. And then this is for my compressor, right? The yellow one's coming from the unit. This is from my thermostat. And then my reversing valve this is coming from the unit, and then this is coming from my thermostat. If you were to follow this orange one, that's the route we're gonna take. This orange one right there, right, orange wire, that one essentially goes all the way to that black wire on the other side of the reversing valve. This yellow wire right here, essentially it goes on that side of the contactor coil. That's it. That's all we're doing. It's just different. It's just the paths that the 24 volts is taking. So in this case, okay, let's take the path. Let's do the easy one first, Luigi, okay? Let's do Luigi. So Luigi, when we have a call for cooling, right? We got on your thermostat, internally, the thermostat, you got 24 volts here, and then it does this, boom. And then that 24 volts is supplied to my yellow and my orange at the same time. So let's take the path of the reversing valve. So I'm gonna be pulling this wire. If I pull this wire all the way, that wire is going all the way on the defrost board. It's not going off of that panel. That orange wire, it goes to my defrost board right there. Oh, okay? It goes right there, okay? Let me make sure you guys are able to see that. Right there. Orange wire, O. Once that O, this orange one, gets 24 volts, internally, yep, you don't see it, but it does. It kind of does this. Internally, it kind of does like a little alligator clip action. 24 volts goes here, and then it comes out from this black one. Guess where that black wire is coming? It's going to. Guess where it's going to? Well, if you said reversing valve, you're correct. And once I pull that wire out, I don't want to spend too much time because I want to just gonna get to the point. I want to show you guys that I'm not lying to though. So if I pull this wire out, it is this one here. You see that wire here, a black one, and that one is going all the way. Let's see if you can see that wire being tugged on. You see the bottom right there? You see? So yep, and it's a black wire. So yes, even though it starts off as orange, it goes here to my reversing valve, to the board, the defrost board. It goes in as orange, and it comes out as black. So yes, Luigi takes that route. So Luigi's gonna go like that. He's gonna go like that. Boom, go like that. Go through the black wire all the way, and he's already here with Rosalinda. Boom, 24 volts to the reversing valve. All right, Mario. Mario takes a little bit of a. He has to go through a couple more bridges. Couple more bridges. So when I have a call for cooling, okay, so let's go here. When I have a call for cooling, we're sending 24 volts, right? To activate the compressor, right, for the contactor coil. Okay, so let's start right here. Boom, it sends 24 volts to my yellow, and it goes right here. Let's see if I can get a better picture right here of this. It goes to the bottom of this one right here, right? This yellow wire right there is coming from this yellow wire. If I were to pull, and I have a zip tie there, but if I were to pull, and I know it's a little hard, but it's coming to this one right there. And just to confirm, that yellow wire, let's get a little closer. You see, Y1, 1 right there. So these wires are going to, so in fact, these wires here, the plug here, the Molex connector, that is all the wires that come out from here, just so you know. But okay, so we're good. It goes to Y. Once 24 volts goes here, it comes out from this Molex connector. Y. Let's see if we can get closer. You see? It might not be the best, but you see? Y. And then we got to follow that yellow wire now. So where does that yellow wire go to? Well, let's follow this yellow one. When I pull it, it goes to the defrost board. And it goes right there to my yellow one right there, right? This is coming from the other board. Okay, so when we go back to this, yep, my yellow one goes like that, right? And then it goes through that other board. You see how it doesn't show the other board? So it can be a little confusing, but it makes it, and it goes all the way to P1-5 to my yellow one from my defrost board. So it goes right there, okay? Okay, this is where I want you to pay attention to. This is important here. So why is it that it comes in as yellow, but this one here, you see that contactor coil, it's blue. Shouldn't that be yellow? Because we have, right? We have other bridges that we need to travel through. So let's see. I'm just going to unplug this so you guys can get a better picture, because if not, it's going to get in the way. I'm just going to unplug that. Okay, so there we go. We got Y, T1, okay? Y and T1. What are these? These go to my pressure switch, my pressure switches. So this blue one here, let's see. So the way it works, once the Y, right, comes here, it sends 24 volts out through this one. And then if my pressure switches are closed, it comes back on my black wire. Let's confirm that, okay? So let's go ahead and take this, let's see, this Y1 here, okay? So that Y1, and then it has to come back. So it's just one long wire going through switches coming back, okay? So the blue wire, right? Let's follow the blue wire here. It goes to that one, And then that one, you see, it gets connected to a black one. If I follow that black one, if I pull on that wire, where does it go to? If I pull on that wire, okay, is this wire here? Okay, just bear with me, be patient right here. Okay, so that blue wire turned to a black one, and this black wire, you see, is going through that high pressure switch. So that pressure switch, remember we talked about it, it needs to be close. So literally, this is what Mario's doing. Mario's going through here, okay, and it's going through the bottom ones I showed you, and then it comes out through the top Molex connector, then it goes here, and then it comes out through the blue one, and then it turns black. You see how it turns black? It can be a little confusing, but it turns black. Boom, 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 boom. And then it goes through my high pressure switch, and I want to show you something real quick, okay? This, guys, is just a switch. Let me go ahead and flip that, okay? That right there is just a pressure switch. So remember, Mario, if the bridge is closed, Mario's gonna come out. You see there's two wires. Mario's gonna go through one wire. If the bridge is closed, then it's like this. It's just gonna be, right now, it's just gonna be, boom. Yep, the bridge is closed. Awesome, I can go through, okay? That bridge only stays open if, remember we talked about it, high pressure switch. If the dirty condenser, the condenser fan turns off, pressure goes up, it opens and rise. But if there's no issue, great. He goes through and he comes down this way. So Mario can continue going through the route. And this is doing its job. If it goes off of a high pressure, it's because you don't want to turn on the compressor because you got to fix the issue as to why the pressure is going higher. But we're good. Let's say we're going through. So, okay, so let's continue Mario's path. So right there, let's see. Here, I got to just find this wire. Okay, so if I pull this wire right here, it goes right here to this black one, and it turns to a blue one. So now let's pull that blue one. Right there, right there. It goes to that one, right? And then it goes to a over here to that pressure switch all the way in the back. Okay, so now Mario came from over there, and he's like, man, I have to travel all the way over here still. Okay, and so that's just the switch. It's just a bridge. So right now, right, if let's say a low pressure switch, if I don't have low refrigerant and I don't have a dirty filter and my pressure stays good, then good, I can go through. The pressure, the bridge is good. It's closed. So Mario goes in and goes out. 24 volts goes in and then it comes out. This is not a load. It's just a switch. So Mario comes in, Mario comes out. You don't see Peach here, right? Peach is already over there in the contactor coil. She's waiting for Mario at the castle, at the therapist, at the rehab center. This is just power in, power out. Mario in, Mario out. So if there's an issue with the pressure, then, of course, that's going to open up. Mario's going to be stuck over here. You got to fix the refrigerant issue so that the 24 volts can go through. But let's say it's good. Let's say it's good. And it comes out from one wire in, one wire out. If I pull this wire right there, it is this one here. This one right there. Okay, this blue one right there. Okay, and then is this one coming out right there. Okay, so this blue one right there, if I pull it out, it turns to a black one. Okay, and you're like, wait, but it's supposed to be blue. Okay, just follow with me, okay? Black. And this black one goes to my, let's get a little bit closer, to, there we go, T1. Once T1 gets 24 volts, because like I said, it comes out from Y from the other board, it gets 24 volts. Then it goes here. And then it goes through my pressure switches. Then it comes back on black. This is what the board does. It then sends from T1 internally. I know you can't see it, but internally, just imagine an alligator clip, right? T1 and T2 internally. It then routes the 24 volts because the switches were closed. The pressure switches, it goes here. It comes out in the blue. And the brown one is my common. Common, 24 volts. So now Look at that blue one. That blue one goes to my contactor coil. So that is the path that Mario takes. He starts off at the thermostat. He goes through this control board. Then he comes out, goes right there. And then he goes through my pressure switches, in, out, in, out. He comes. And then he goes to T1. And then that gets 24 volts. Then he comes out on the blue, and he goes to peach. Now they completed a circuit because it takes two to tango. They're both at the load. They're so happy they were able to fix their marital issues. Current is going back and forth. That gets pushed in. High voltage goes through. That is the route. We got to figure out the route for all low voltage. And this is simply how it takes it in a simple way, right? Even though there's two boards, you might have one board. It's always end goal is to go to that contactor, right? So we just talked about it right here, right? Right? It goes through here, right? You see? It goes through that defrost board. You see right there, it goes to my pressure switches. And then those matter right there, right? Those letters, the blue wire, you got to pay attention to all those. Then T1, and then it comes out of T2, which I showed you. Blue wire going to T2, right? So another way, and this is where having a meter helps. I know this is not a class on using meters, but another way you want to find out, a little pro tip here, another way you want to find out if you have good pressure switches, or if Mario's gonna be able to go through all the way. So these right here go to my pressure switches. So I can just pull this wire out, these wires out, right? And then have in mind, right? Look at that meter right there. If the light on the top turns green, let's see. You see? It's turning green. I'm just testing my lead. So let me go ahead and check it right here. Check it right there. Check it right there. You see? It's green. That means I have no refrigerant issues. You see? I have continuity. That means all my bridges are closed. So the meter sends a little bit of current going through, and it's able to make it back because all my pressure switches were closed. This is another way you can find out if all my pressure switches are good going that way. So when Mario goes through, he's going to be able to go through and then come back to my board, which my board then sends 24 volts to that contactor coil that turns on the compressor. My reversing valve already has Luigi and Rosalinda. They already have 24 volts. And then I have a call for cooling. Okay, so this is more on the troubleshooting side, but let's say everything is wired right. You figured out how schematics work, but this contactor coil can be bad. Remember, there's three things to a circuit. You need a load, you need current, and you need potential difference, or your voltage. So the way I like to do it, you see this plug here that we were talking about earlier. This blue wire, my 24 volts, goes to the 24 volts that powers up the contactor coil. So you put it on continuity, and then you have to use the little leads, right? You can use the thick ones, but sometimes you can damage that and open it up more than what it needs to. But try to get the part that, like I like to get just that part right there, that blue part, the part that's right there. This part, because I'm touching the exposed part. I go there, and this one I have to read continuity. You see, I'm getting a path. So even though, let's say, the board sends out 24 volts through here, through this wire to there. Well, if this wire is bad, it's nicked, it's cut, well, it's never going to make it over here. So remember we said we need voltage, right? So voltage, so we need potential difference. Commons are already there. If my wire is in good shape, then I'm going to have that potential difference. And then through the copper, I got current going back and forth. That can be one thing. Another thing too, from my experience, you want about 13 to 21 resistance when it comes to your coil, because this is a load. This can also be bad. So let's go ahead and test that. You see right there, I'm reading about 14 ohms. So it's still in good condition. But if you read open line, or you read like 5 ohms or 3 ohms or 0.5, then it's a bad contactor coil. So yes, schematics is one thing. You can get that down, but it's important to understand that for a circuit to work, you need your voltage, your wire has to be in good condition for the current to travel back and forth, and your load has to be also working. So I understand if the ladder wiring diagram was a lot for you to digest. I get it. It's a lot. It's a new concept. But I really focused on the low voltage side of things with the cooling. At least with this system, it was a heat pump. All we're doing is making sure that our common makes it to one side of the coil, and then the 24 volts makes it to the other side. So, but still, that can be a lot to digest. In fact, there is so much we could have gone over more with the ladder wiring diagram, but it's just so much. But if it is a little bit still a little bit intimidating, overwhelming, try reading or going over connection wiring diagrams. They're also known as pictorial wiring diagrams. I thought to go over the latter one because you tend to see more of those more often out in the field. And if you understand ladder wiring diagram, you will for sure understand this right here. Look at how easy a connection wiring diagram is. And by all means, if this makes more sense, if you want to start off with these, then go for it. This is a lot easier. But we gotta identify your transformer. So you see, your high voltage is here, but you have a little bit of low voltage on this side. The ladder wiring diagram was high voltage on top and then low voltage on the bottom. So this one, you can actually trace where all the wires go to. So for example, right, for my common, if you were to follow my common, on the board, it actually tells you where it goes to all these commons. They're all commons. This low one goes to my ECM. That's the 24 volts that powers up any of the speeds that you want to use, right? And then my 24 volts goes to the R on the board, and then it goes to a 3 amp fuse. And then, although this line is not there, but I drew it because that's where it goes to. It goes to the little Molex connector, and then all these wires that you see coming out are all those wires that were coming out from the unit when you first install it. It is those wires there that come out, and then you got to bring in your thermostat wires and wire nut them. So, but like I said, this is where it goes. It goes to R, boom, it goes to my T-stat. So this here right here is my T-stat. Oh, actually, it's already written there. So, right, the temperature switches. So let's say I have a call for cooling, right? It sends 24 volts to my yellow one. And look how it is the same as the ladder wiring diagram. It is the same when you saw me with Mario going through the wiring in the unit. It goes through the yellow wire, and then it goes to the Y1Y on the board, and then it comes out through the other one, Y. And if you follow that, it goes to my defrost board on the Y, which we were able to see on the other board, on the other clip. And then it comes out through Y1. It goes through my pressure switches, and it comes back to my T1, and then it comes out of T2 as the blue wire going to the other side of the contactor coil, because peach is already there. So that's what's nice about connection wiring diagram. You can literally trace the wire to see where it goes, and it's a lot easier to understand. Even the high voltage, you see, once this receives 24 volts, then it does this, boom. And then my black wire, my line 1, boom, completes the circuit, and then it sends, and then it turns on the condenser fan and the compressor. So with the connection wiring diagram, you can literally trace where the wires are at and what colors they are, and see where it's at, and then boom, it's exactly like that. Of course, the wiring's a mess. You still have to follow the wiring, but this one's a lot easier. But I just had to go with the ladder wiring diagram because that one will help you understand that all you're doing is using low voltage to control when you send 24 volts to the contactor coil to then send high voltage to go through and power up the components. And maybe in the future I'll do another video on connection wiring diagram. But this is all there is to wiring diagram. At the end of the day, can I take these two wires? Right? Can I take 24 volts in common and go straight right here? Just skip the whole thing and just go right there. Right there. Boom. Yep, that would work. But the unit will stay on all the time. That is why we need to reroute it through pressure switches, through your temperature switches, which is your thermostat. The comment does go there, but not the 24 volts. So if there's anything you're gonna get out of this video, is that your high voltage, you don't have to worry about it. It's all wired up. If anything that you got to replace is your capacitor because they go weak, your contactor coil go bad. Pitted contacts also can go bad. Your compressor, your condenser fan, yep, they can go bad. Your indoor fan motor, your ECM, can also go bad. The wires themselves, yeah, they can rub off and cause your breaker to trip, but rarely would it be the wires. It's more the components that allow power to go through. Down here, you're just using low voltage. So yes, your 3-amp fuse can pop because hot and common touched each other. The Bloods and the Crips, they're gonna fight. They must meet at the rehab center, Homeboys Industries, or Mario and Peach. Peach is gonna beat up Mario. But if they go to the therapist, marriage counseling, they can work it out, and they're so happy. They're going back and forth. Bloods and the Crips, they're in the rehab center. They're awesome. They're getting along. Boom, 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 boom. That's the current flowing back and forth. That coil energizes, allowing high voltage to go through. So down here, we're just rerouting the 24 volts using temperature switches. In this case, a thermostat. Your pressure switches. Yes, even the boards. It's just power in, power out. That's all we're doing when we're trying to understand wiring diagrams, whether they're ladder or pictorial. Yes, this video was a lot longer than usual, and there's a lot of things that I left out, but realistically, if I post a 2, 3, 4 hour video, many won't watch it. And also, I really wanted to try to make this video under 30 minutes, but if I push for that, then there's certain concepts that you would have not have understood, and it would have made it harder for you to understand schematics. So yes, this video is a lot longer. If you need to go back to a certain clip, go ahead by all means. If you see the way that I recorded all the clips, it is in a way so that you watch it from the beginning, you understand certain principles, and that will lead you to the later clips that goes into the schematics. So try to follow that suit. But really, when it comes to schematics, when we're working with conventional air conditioning systems, gas furnaces, heat pumps, not a VRF, not an inverter, not a mini split, a conventional air conditioning system, all we're doing literally is this. Is the bridge open or close? Open or close. And you can even do it whenever you go to a diagram, a schematic, go with your hand and see, okay, right here is the bridge open or close. Because if the bridge is closed, when it comes to the low voltage, it sends low voltage to the coil, which then allows the bridge to close and sends high voltage to go through. So yes, there is differentiating low voltage and high voltage, but either examples though, is the bridge open, power is stuck. Is the bridge closed, or right, or with our hand closed, power went through. It's going to be doing something. You see how pressure switches, your thermostat, how all that tied in with the low voltage. With the ladder wiring diagram, you're able to see how on the bottom you have your low voltage, on the top you have your high voltage, and what differentiates both is your transformer in the middle. And your pictorial connection diagram is a lot easier because you can literally follow the lines as to where the power travels to. So yes, this was a light class on schematics. Like I said, I wish I could have kept it a lot smaller, but it gives you a basic foundation. So if you go to units that are single phase or 3-phase conventional air conditioning systems, this will help you understand and have a basic grasp on how to read schematics. Friends, I hope today's video helped you out, and I'll catch you all on the next one.